the last step of the big homework, I promise, and I'll get it done today. And be careful, because every steps, I think I give you the material. You just need to make sure you can visualize it. Don't just plug and play. I plan to put the tricks on the data set. Okay, I reload the material, and here is what we have. Okay, step one, everybody raise hands. You know how to get those parameters from a SAS output, right? You can have the SAS output without any variable or with some variable. Everybody agree? You can do that. Okay. Please, first, can you do that? Do proc distribution equal to Weibull, because Weibull is the most common one. And I'll talk about other distributions, but if we go through this clearly, we're good. Second, okay, I already showed you how to use Weibull scale or Weibull parameter, but you're going to end up getting the alpha and tau, and why we need alpha and tau and lambda, because those are the variable we use algebraically. And how to get that, I show you the example, how to turn SAS output into that. Problem? No problem. Okay, yeah. The third one is remember, okay, when you have parameter, what will be the value? You need to do a sum product on top of the intercept. And what is the product here? Usually, I will tell you, based on the policy, the SAS policy, I will tell you what is the individual characteristics. Okay? So in this case, I'm saying that I will have finance, 30 years old, race 1, work experience 0, marriage status 1, all that stuff. So once you times that, you will have this things done. Problem? No problem. You got it. Okay, finally, please be careful here that when you do this, it's beta 1 times x1, beta 2 times x2, beta 3 times x3. But remember, we did not add beta 0, so you need to include beta 0. And that's part of the reason I show you the example here. For this example, I have this originally the intercept, because when you have no parameter, you still have an intercept, right? Beta 0. Okay, next. Okay. Once you've done that, okay, you have your lambda and off things here. I show you the equation here. Okay. First, ft equal to this equation. First equation is our old equations of Weibull distribution. Agree? And 1 minus ft really equal to what? 1 minus ft equal to st. So this is your st equation. The second equation is your st equation. And then if I take log and log again, sooner or later I can turn this back, revert into an inverse function. So what I did here is I show you 2 examples of inverse function, with variable or without variable. Let me show you the with variable here. Okay, and here st equal to exponential negative lambda t is this equation, and then ft is 1 minus st, and inverse. Okay, and for the inverse, this always happens because 0 is infinity, so you don't see 0. But after 0, see, once you do inverse, you should see that you should recover f inverse t equal to t. Okay? So if I do this, okay? I'm just want to have another set. Okay? So now I have another set done without those variables. But with the variable here, if you plot it, okay? You plot those things. No, I'll just plot until here. Insert chart. You should see the lambda, the reliability coming down, FT going up, just like the numerical, fictional example we did before. You should be able to do this without any problem, okay? And then you can do this with this set, but you can do this for the other set too. And here, let me just copy this example. And what I want is to do this. Okay? And if we do this, No. I did I changed the t value. Originally, the t is jumped by 2 or 3. I can't remember. Now I just do it. The t is just 1 by 1. See that? Okay. And why I'm doing this? One is you can always plot it, right? You plot it. You know that you should have 1 going down, 1 coming up, and if you have 1 going down, 1 coming up, you know you got it right? FT is dropped to increase monotonic to 1. ST is coming down. So here are the 2 sets. And the second thing what I did is I like to put an inverse function here. Once I inverse, I get the same number, recover the t back, I know I got it right. Agree? See, if my mass is right, I went to the transfer function and transfer back, I should get the same number. Okay, so far so good. Next, okay, now if I have everything's done, let's go to the scary part. Okay, the scary part last time I already showed you. This is to the SAS versions to get the integration done. So if you go to SAS, okay, this is like what we did before in Excel, except now we're using SAS to help us. But the things, here at the very end, usually you put a run, because if you don't put a run, it won't run, okay? And, okay, so here are some parameters I run, and here is the same things. And when I'm done, okay, people look at here, okay? What I did is, I'm doing integrations from 0 to dot p is to positive infinity. Dot n is to negative infinity. We don't have negative, okay? So to 10, to 20, to 30. And then I did this one is from 0 to 10, 0 to 20, 0 to 30. And while I'm doing this, watch. First, if you have an integral, from 0 to infinity, okay? From 0 to infinity. You're integrating 0 to infinity of your ft. This value, okay? 0 to infinity, this value, 223.8, okay, is your mean value on average, how long people will last. 223 days, okay? So on average, I'm basically saying that start from your VAR, actually start, when you say this is 0, and then your beta is 100%, okay? You get 223. Now, remember what I did is what? I'm moving, I'm using this one then. Let me do it, 1, 2, 3, 0. 1, 2, 3, 0. Okay, people, watch this. I'm doing it with variable. Okay, so with variable, look at it, the curve. If I start from here all the way to the infinity, I'm basically integrating, okay, 0 to infinity of my survival function. So I'm just having my entire I3 done. And that one, I get 223, okay? But now, if I'm doing 10 to positive, to infinity, 10 to infinity, I get 213.9. 213.9, okay? It started from cut at 10. So I don't count anybody before they survive 10, right? So the integral will be started from 10, somewhere around here, and integrated over there. So here you should have 10, and then here is integrating the reliability function, you know, or the ceiling value from 0 to infinity, from 10 to infinity. And the next things you need to do is saying that, well, then what is my beta? My beta value should be M16. Why M16? Because if you look at M16, it should be somewhere around here. What is M16? Is your survival function, right? And survival function really is from where to where? From the ceiling to here. One step at a time, okay? Think with me. First of all, overall average is 223. On average, every inmate survived 223 days. But now I'm only care about those people can survive at least 10 days. So my CVAR value should be more than 223, agree? 223 means from 0 to everybody. But now I'm talking about the value of, hey, at least survive 10 days, and then I'll check on you. So this value is a little higher. But how much higher is this? 10 and beyond. So 10 and beyond, so I need to figure out what is my beta value for 10. My beta value for 10, okay, for 10 is somewhere around here, right? From ceiling to here. So I'll say my beta value is probably 80% or something. And look at here. My beta value for 10, oh, it's actually very high, is 98%. Okay? I must did something wrong. So my 10 is probably here. Oh, okay, this is 150, yeah. So the beta is from here to here. So my beta value is very, very high for 10. And now I adding up this value is 226. Got it? Next, if I said, hey, I don't want to wait at 10. I want to wait until you reach 20 weeks, and then I'll check on you. 20 weeks is even better. Oh, here I made a mistake. Here it should be 20. Agree? And here should be B68. This is 20. And then, and what is my beta? My beta is 20, okay, is about 0.97, okay? So, no, M26, okay, got it? Finally, 30, and same thing, figure out the integral, I3, divided by the beta, okay? This is not an insurance example, so if I'm talking about wind turbine under different working conditions and so on, a lot of time we will compare the increment and decrease and try to figure out what is the right warranty level we can give people, okay? And I don't want to get into the how to find the optimum CVAR. That is almost like a dissertation by itself. But can you guys figure out this mental accounting now? Is I can set up my VAR at any point, and then when I set up my VAR at any point, my beta need to be fine, and you can find this. And so I have two questions for you. Can everybody see that the CVAR value should be more than the mean average life value, 223? The second part, can you see that when you're pushing your VAR out, it's not like the more you push, the more CVAR you're going to gain. See here? It's kind of dropped a little bit, by a little bit, okay? Next, I would like you to think about all the game I play here, okay? Remember I have a 223 done, overall average, right? So if I do my integral from 10 to infinity and also did an integral from 0 to 10, add the two pieces together, I should end up with my mean value. Agree? Because I'm doing integral 0 to 10, 10 to infinity. Same thing, can I do a 0 to 20, 20 to infinity? So this is another double check you can have to make sure that your integral is okay. Follow me? And this is the steps I'm doing. Next, okay, I did a tricks is sometimes we can do the integral this way, okay, vertically, coming down, going up. And sometimes people can do the CVAR, VAR by doing the integral from the beta side, horizontally. So here I'm just, for fun, do a horizontal example. And to show you, I use the same equation, but this time I set up my beta value and say, hey, give me 80%. And once I set my beta at 80%, okay, and when I run the integral, okay, when you run the integral, you will have this 3.44 integrating from the 80% up. And so what I did is, hey, if I integrate it from the 0 to 1 from beginning to the end, or I added, like here, from 0 to 70%, 70% to 1. You guys follow me? Can I do the integral from 0 to 1 this way? I can, right? You know, can I do an integral from 0 to 1 for the red curve or for the blue curve? Either way will be fine. But when I did the integral, I chipped them this way, one by one. So I can do one integral for 70%. Oh, this is almost 70%. So if I do an integral from 0 to 1, and then I do an integral from 0 to 1, and then one integral from 0 to 70%, and one integral from 70% to 100%. Look at the value. Total 0 to 1 is 344 or 344. But if I do it this way, 241 and 103, add them up together, I get my 344. Okay? In the old day, I cover Choquet integral, but generally if you remember your Cal 1, you do an integral vertically is called Riemann integral. You do it horizontally is called Lebesgue integral. Okay, so I'm going to refabricate the prisoner's data. Okay, so everybody, if I fabricate a set of prisoner data and I ask you to compare with support, without financial support, compare different variable, can you plot them in two different colors and show me if there's a difference or there's no difference? So which variable makes sense? You can do that, agree? Using log rank test. Senorita, okay, good. Basically, you follow the same step, but you just need to think, okay, does this make sense? Second, in live regressions, okay, you will have different variable, but you will end up with different parameter. And you should be able to do a integral or a set of plot for live regression based on no variable, or based on a set of variable I'll give you and the characteristics, and you can build your lambda function and your t function. And once you do that, okay, you should be able to plot your FT and ST accordingly. Okay? And once you plot the FT, ST accordingly, the rest is, okay, now I know that for this individual, this is his survival curve, or this is his CDF. And I can estimate every characteristics about their CDF, how quick they're gonna reach 100%, or how quick they're gonna run out of their juice. Next, we will say, okay, when should we check on them? So I can say, check on them at 10, or 20, or 30. How did I come up with those when I'm gonna check? Usually is, they'll say, domain knowledge. And where the domain knowledge coming from? Interview the expert. The expert said that, for example, have you guys ever seen a baby start eating solid food? Using baby, those baby food? I just recently visited, one of my students having a baby, been a while. And just, now is about 8 months old. they are start getting supplement of solid food. And I basically said that, well, it's not teasing yet. How did you decide this is the time to start giving banana, yam, or that stuff? And they just said that, the grandma say so. And the grandma, you have grandma from the father's side and from the mother's side. And especially if you have different culture, what will be the issues? One will say, oh, this is too early to have the solid food. One will say, nah, this is good enough. No, it's good enough to. So the psychophysics is, you only know that if you check the baby based on the growth, based on all the physics, the doctor will say, well, this is the potential for this 95 percentile male baby, and so on. Those are doctors' decision based on the physical observation. But sooner or later, grandma psychophysical judgment play a role. I think this is good enough. Should start trying, baby food, solid food. One will say this is too early. How late is too late? How early is too early? And so that's why a lot of time we have the VAR value play a role. So I will probably do everything similar to this. And so what I would suggest you to do is go through the steps I cover every time. And you can repeat everything and say, what did he do here? What did he do here? And then try the new data set. Okay? That will be the homework. I think I give you all the cheat sheet needed to do this. Okay? Now, let's do something else. Let's. Huh? I'll be honest with you. It will be easier for you to develop your own spreadsheet. Because a lot of time you want to double. Well, let me put it this way. It doesn't matter because at the end, all I care about is I see the FT coming down, ST going out, inverse is the same, and the double check value, however you do the integral, 0 to infinity should equal to where you make the cut and beyond the cut, the I3. You agree with me? Yeah, so if the double check that doesn't make sense, I know something is wrong, okay? And I was trained this way even when I worked for airlines. And a lot of time I have all the flight plan stuff coming in at the end. All I did is fuel, food, everything's estimate. And the total payload should be this much. The airplane should be this much. The total flight takeoff weight should be this much. And if I look at a number and then ask cargo, how much you give me, passenger, how much you give me, and I cannot add up together, I know that something is wrong. So this exercise actually, what I'm trying to say to you is that when you graduate and work in the real world, whenever there's a large, very many steps stuff to do, what's important things? Every step or every other step create a double check mechanism. Because if you create a double check mechanism, it says that if this is true, this together, this should be the total number. You don't see that number or the plot doesn't look right, you know that either people give you the wrong info or something is fishy in your calculations, okay? Yeah, create double check mechanisms is important. And so when you do the spreadsheet, use mine and then do your own. You should see the same benefit, okay? And next, let me get to the reading material. Okay. Now, chapter 3, we're done. Okay. Oh. Okay, on chapter 4, and I already explained to you once, okay? You can model life or log survival time, and time is exponential of all the stuff, and you can model them as your hazard function, okay? In Weibull, that's why Weibull is so popular, is that in Weibull, your survival functions, life regression, and proportional hazard model, their regression value are exactly the same. Here, if you divide it by sigma, everything divided by sigma, you will get your proportional hazard model, except you need to change the sign, because good for hazard, bad for life. Good for life, bad for hazard. Okay? And when you run this, you can run this for log normal. You can run this for different distribution, exponential, and so on. And one thing's important here is that your error term, okay, this is beyond the scope of this class, but I'll just give you the lip service here. In your regular normal regression, general regression, you're using least square. The error term shall follow what distribution? The error term in your experimental design should follow what distribution? Victoria? You have a central station or regression, whatever the leftover should follow what distribution? Remember? Huh? No. In your experimental design, I have a regression or I have a different level of ANOVA table. The leftover error term should follow what distribution? Normal. Good job. But what we usually say, if it's not normal, then we need to do transformation. But in regression, in live regression, it's not the case. In live regression, since we're doing maximum likelihood, okay, and here is basically said that if you have your distribution is Weibull, your leftover is extreme value, and if two-parameter extreme value, and if it's norm exponential, you will have one, and then if it's gamma, it's log gamma, log logistics, and so it just let you know that your error term is not normal, okay? And there are people trying to find a normal distribution that's hard. Here, the things I would like you to pay attention is the log likelihood function here. We would like to maximize it. And here, I'm basically trying to show you, here is the part I just mentioned. On page 69, highlight this. Beta star equal to negative beta divided by sigma. On page 69, this is the things I'm trying to tell you. Usually, we only say that, good for hazard, bad for life, good for life, bad for hazard. But in Weibull, with all kinds of shape, all you care about is that as long as you have a Weibull scale parameter, your sigma here, your beta divided by sigma will end up as your hazard function equation. So in other words, if they're both 0, no hazard, no life. Good for hazard, bad for life, good for life, bad for hazard. So they always inverse sign, and the difference is based on the 1 over sigma. Okay, that's your Weibull scale. Okay, next, I would like you to look at the following. Okay, I'm having them doing in live regression proc here. Let me pull this one out. You guys remember when I do regression here? I can let distribution equal to Weibull. I can let distribution equal to log normal. Any function I can use, right? All the distribution, the transfer function we can use to check. SAS, no matter which one you use, will give you a set of output. But remember, in your design experiment, since it's follow normal distribution, the leftover. So the sum of square can be compared as chi-square over chi-square. So you can say that, oh, which one is better because the F value is getting bigger and bigger. But for this kind of regressions, I cannot do that because they all have different error term. So you can only compare them using log likelihood. And here is the log likelihood I would like you to think about, okay? Before I go into the math, I just want to first jump to the conclusion first. Okay, here. They all have log likelihood value. This is the value I would like you to think about. It's on page 89. Okay? And where those values coming from is every time you let a distribution equal to log normal, whatever, it will give you a value. And now we're basically said that, well, you can ask, when we play with the Excel, you know that sometimes add 1 parameter, sometimes add 2 parameter. They all have all different shapes. So now I'm comparing the performance, the goodness of fit, based on what? Different distribution. I'm comparing orange with apple. I cannot use F-test to do that because I don't have a normal distribution error term. So the way how I do it here is this, okay? First thing first, here is distribution equal to exponential. Here, let me show you this, okay? Here is equal to, here, let me just run 2 for fun. Okay, and I don't have any variable, okay? So that's the things. If you want to compare 2 distribution with 1 variable, should be 1 variable. If I have a finance here, okay, I should have finance here too. You guys follow me? You cannot compare 2 distributions and say, oh, I'm going to compare you with 1 variable and I'm doing no variable. That's not fair comparison. So you both have, say, 1 variable. And so now if you run it, you will have a log rank test value right here. 335 for log normal, log likelihood for 334 for this one. So negative 334 versus negative 335. which one is bigger? Negative 334, right? So just by simple comparison, I can say that, YBO is better than log normal. But is that comparison fair? That is the part I would like to talk about here. If I have a bunch of distribution, 325, 319, here are a bunch of log likelihood value. The log likelihood value I have here are using all the variable. Okay, young lady, which one is the best distribution based on the table here? Among the 7 distribution here, which one is the best? Which one is the biggest one? There are negative value. Which one is smallest absolute value? The last one, right? Generalized, because this one is what? 31938. Absolute value is the smallest, but it's the maximum value because we're using negative. Okay, so the thing is that if you only use that considerations, generalized gamma probably will win every time. You guys know why? Because they have 3 parameters on top of all the beta 0, beta 1. So the more variable you use, usually you will get better fit, okay? So this is almost like saying this, okay? You try to model me, my behavior. You use 10 variable, okay? And then your log likelihood, okay? Now let's just don't use log likelihood, just say percentage-wise. You can model 80% of my behavior using 10 variable and parameters. And you can also model me, okay? You only use 2 parameter and 1 variable, so 3. But you can model 75% of my behavior, okay? So which model is better model? Why? Because you use very few things, you can model and control everything. So same thing here. They're saying how to compare orange with apple. The way how they did it is doing this almost like doing a bus stop or multiple comparison. So what they did is basically first copy paste. Oh, because they're using log likelihood and log and value less than 1, causing that problem. But still multiplication, you try to find a maximum fit, the maximum likelihood. Concept still there, but the computation is negative. Okay? But what I'm trying to do is this. Okay. I did it wrong. Okay, usually this is like multiple comparison. Paste special, transpose. Okay, so what you do here is using this guy minus this guy, okay, and then E5 you lock the row. And here you lock the column. Okay? And then you can create a table of multiple comparison. And, oh, I don't need the last one. Okay, so see here? Oh, I need to double check. 325, 319, 322, 319, 319, 319. Okay, I got it right. So you can see, okay, exponential compare with Weibull. Exponential compare with Weibull. The difference is 6.45, okay? And, oh, and because the comparison is two-way comparison, so I need to divide times 2. Okay? And so the first value, let me use this. Exponential compare with Weibull is 12.9. Okay? And then exponential compare with standard gamma is 12.74. Okay? Exponential compare with generalized gamma is 12.9. Okay? And then Weibull compare with generalized gamma is 0. Weibull log normal compare with generalized gamma. Weibull was generalized gamma. No. Weibull was log normal was generalized gamma. Log normal was generalized gamma is 6.62. You guys see where the page 6.9, the value coming from? Yeah? Everybody see that? The next things I will ask you is that, can you see where is the comparison coming from? Okay? So, based on this, okay, you can have a bunch of log likelihood and say who is the best. And so far, okay, you probably will say that, oh, look at here, okay? The best one is generalized gamma. But compare with generalized gamma, exponential is really bad, okay? But Weibull compare with generalized gamma is 0, okay? So generalized gamma is the best model, right? Because it's 12.9. But Weibull compare with that, the difference is 0.02. It's really, really small. Now, which model is the best model? When just like you will run a bunch of models, and when you run a bunch of models, all you care about is this log likelihood. Which one is the best log likelihood model to use? You sure, as always, try to find the largest value. But then, if the largest value here, okay, Weibull is number 1, okay? The champion is this one, right? But champion is this one. And when you compare the champion with generalized gamma, they're almost the same, equal. Okay? Which model is better model? They both say model 7 parameter, 7 covariate. But parameter-wise, Weibull only have shape parameter and scale parameter. Generalized gamma also have one more parameter, got 3 parameter. So in this case, generalized gamma is much better model because it used less parameter. Okay? So this is the documentations that I would like you guys to try. Is I'll tell you that, hey, give me 10 model. Here are the 10 model I would like you to compare. Usually, okay, for example, in this case, my exponential value is 325.83. Okay? What if my exponential value, okay, is 320.2? If my exponential value is 320.2, you know what I probably will do? I probably will choose exponential, because how many parameters you need for exponential? Only one. Okay? So here are the things you need to remember. Usually there are the pressure from the domain knowledge people. They like to talk about, oh, I have this magic medicine. Is this magic medicine is almost like snake oil. It can treat this, can treat that, treat everything. But when you ask how many things in this snake oil or whatever, they'll have 20, 30 tons of variables in there. When you have so many variables, and then you have so many interactions of those variables, and then the parameters, at the end, even that things work, you really don't know which is the true interaction or things you can bet your life on it. So keep it simple, stupid is the take-home message of page 89. Always use as few parameters as possible, as few covariable variable as possible. In this case, in the example I give you, okay, the inmate parole example, people actually check at the end, what can keep people out of the jail. The study was a very, very tragic study. The conclusion is nothing works. But if now is voting season, do you think politicians would like to tell you that nothing works? They always want to tell you, oh, I have this magic, I can make something works, okay? Yeah, and let me get out of this. No, I don't think I need to get out of that. Let me go to the how this is modeled, or how SAS did it. Okay, how the log likelihood negative value coming from. Okay, so remember I have a bunch of failure, and then I have a lot of sensor, which is survival, and then the data set, every observation, either sensor or either failure. Okay, sensor value is multiplied by their ST. Why? Because at least we know they survive until they walk out of the deal. So your likelihood function is multiplication, either FT or ST, but not both. So this is the tricks they did, is that they have a switch function. If you're using sensor side, you're using delta equal to 0. 1 minus delta becomes ST. And this side, delta equal to 0, the left side equal to 1. So every observation, either survival model this side or failure model this side. Multiply, 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 multiply. And then, of course, I can take a log of this. And here is your part. Log likelihood value with a bunch of value less than 1. Multiply, multiply, multiply a lot of less than 1 value. It will become smaller and smaller. Agree? So that's why your log likelihood become negative. But even log likelihood become negative, the multiplicand itself will like to pick the biggest one I can pick. And the example here, they said, for example, is exponential, so FT, PDF look like this, ST look like this, and I'm gonna multiply them many, many times. And I need to find this value, try to maximize it, and you can generalize this model by compress the expression into this, and take the log, it become beta, or the parameter, and then this. And first derivative equal to 0, second derivative for maximum is less than 0. So you will model two matrices. One matrix is called Jacobian matrix. The other matrix is called Hessian matrix. And when you do the inverse, one's called Hessian, one's called Jacobian, or they call it gradient or score. It's the same thing. And you model it, it will end up with this expression, and the maximum likelihood is equal to the improvement of this. And this is the solution, what SAS give you, okay? If you guys want to go for graduate school, for all the maximum likelihood for very, very complex distribution, how to find approximation right now, using machine learning, the deep learning convolution neural network to find the optimum beta is still hot, okay? Because people always find another distribution, joint distribution they want to use, okay? So your homework are two-part. I will give you a new set of data. You need to find the parameter, you need to find the plot, and of course, I'm not gonna do 20, 30. This time I probably use 100, 200, 300, and ask you to find a VAR and CVAR, and got everything's done. And of course, I will also say that, hey, at the end, I would like you to compare this many parameter using different distribution. Tell me which distribution is the best distribution to use, okay? And this large set of homework, I'll give you 2 weeks to get it done, okay? Okay, see you next time.